And then another factor that affects water, that water can do, but actually any solution can do this, but frequently we talk about it in terms of water, is called the colligative properties of any solution. And these are unique properties because they're dependent not on what you dissolve, but that you have a solution. So colligative properties matter if you have a solution versus a pure substance, and they matter on how much of the material you dissolve in a solution. So if you have a solution, how much stuff do you dissolve in the water? So a salt water solution will have a certain set of properties, and a sugar water solution will behave the exact same way as long as those two concentrations are the same. And a more concentrated solution will actually give you slightly more increased properties compared to a lesser concentrated solution. And that's four different things that can happen. So you get a change in the boiling point as you add more solute to a sample. So if you have a solvent sample, a sample of a certain solution with a certain solvent and a certain solute, as you add more and more solute, as you dissolve more and more stuff, the boiling point goes higher and higher and higher. And as you add more stuff to that solution, the freezing point gets lower and lower and lower. So basically these remain a liquid state for longer. They boil at a higher temperature and they freeze at a lower temperature. And two other factors that come up are vapor pressure and osmotic pressure. This has to do with kind of the pressure that that liquid places on its surroundings. And these are more important in terms of cells, in terms of dehydration and rehydration of samples. So when you're talking about keeping yourself hydrated, these come up versus the other ones are more to do with the temperature at which things boil and freeze. But what happens is if you have a solution of pure water, for instance, so pure water solution would boil at a certain temperature. And in our case, it's going to boil at 100 degrees Celsius. So at 100 degrees Celsius, the water would normally boil. And at 0 degrees Celsius, the water would normally freeze. But if you were to add salt to water, then the water would boil at a higher temperature. It may boil at 101 or 102. But also if you were to add sugar to water, it would boil at 101 or 102. Or if you added ethanol or methanol or mint extract or anything that you add to water, as long as you create a solution, then you actually change the boiling point of the water, and the water boils at a higher temperature and freezes at a lower temperature. So normally water is a liquid from 0 degrees to 100 degrees, but salt water might not boil until 104 degrees Celsius. So now we boil at 104, and maybe we freeze at -2 degrees. So now we're a liquid from -2 to 104. So this is a 100-degree range over here. And then on this side, it's a 106-degree range. So now we stay a liquid for 106 degrees when we're a saltwater solution compared to a pure water solution. And the same thing would happen with sugar or with antifreeze compounds or with ethanol or any molecule that you add to water. And that's why you can do all sorts of different ways to change the freezing point or the boiling point of water. If you have a car and you're worried about the lines in your car freezing, so the water lines in your radiator, you add antifreeze to it. Antifreeze makes the water freeze at a lower temperature, but it also makes the water boil at a higher temperature. And since the radiator is keeping your car cool, you don't want the water boiling, so you want it to boil at a high temperature. And in the winter, you don't want it freezing, so you want it to be low. So it does a dual purpose. It keeps the water from freezing or from boiling. And all these different materials. So radiator liquid, antifreeze is usually an alcohol, so you could take ethanol, but even things like soda. So soda has sugar and carbon dioxide in it, and if you were to take a glass of water and try to fill up an ice cube tray with it and put those in the freezer, and then fill an ice cube tray with water and come back in 20 minutes or an hour, see how much of the water is frozen and see how much of the soda is frozen, and you'll see the water freezes faster and the soda may not freeze at all depending on what temperature your freezer is set to. It may not freeze at all, or it may freeze more slowly. Same thing if you try to take juice or some other liquid and try to freeze it. Liquid juice is a concentration of water and various sugars and other molecules in it, and it's going to be a solution, so it's going to freeze at a lower temperature than pure water would. So these are different properties that solutions have, and any solution has this property. A solution will freeze at a higher temperature, a lower temperature than the pure solvent, and a solution will boil at a higher temperature than the pure solvent, but usually we talk about these in terms of water because that's the thing we're interfering with. But you could do it for any solution. So this is happening mostly because these solutions are basically blocking water from forming their own shape. So if you were to look at what happens when you dissolve something like salt in water, the salt molecules and the chlorine molecules are forming these little interactive spheres with the water. And now the water is not able to interact with itself as well as it interacts with the chlorine, because chlorine is really good at interacting with water, really strong negative charge. And that's causing the negative chlorine to interact with the positive side of water. And now this water molecule here is going to interact with the chlorine and not as much with its neighboring water molecules. And that means that when the water tries to boil later, this water molecule is holding on even tighter. It's not only being held onto by the water molecules, it's also being held onto by the chlorines. So those chlorines can help hold the water molecule in place. And when the water molecule tries to evaporate, another thing is helping hold the water molecule really tight and keeping it from going away. And then when I try to freeze the water and I try to form those perfect hydrogen bond shapes, these chlorines are going to get in the way and these sodiums are going to get in the way, and I can't form those really cool crystals to make the water form the perfect shape and form an ice crystal. So it cools down a little bit slower and freezes a little bit slower. But the important thing for these, it doesn't matter what I put in solution. As long as it's something that dissolves, a chlorine is really good at blocking this, but so is a K plus molecule. So a K plus could interfere just as well as an Na plus. A Cl minus or an F minus can both interact just as well with each other. So a negative fluorine or a negative chlorine can both block and interact with the water molecules the same way. So it doesn't necessarily matter what I dissolve, it matters how much I dissolve, because just one or two molecules is going to be a very small effect, and more molecules is going to be a greater effect. So that's the important part for these. It's not necessarily what you add, not the nature of the molecule, but the number of the molecule. For these. So whenever we look at the raise of the boiling point or the lowering of the freezing point, it depends how much molecules you actually add there versus what molecules you add. As long as it goes into solution, it's going to have that effect. So we kind of mentioned the different points here. Again, the freezing point is going to go down, the boiling point is going to go up compared to the pure solvent. And there's actually equations that you can use to figure this out. So if you wanted to figure out kind of how much does the boiling point go up or how much does the freezing point go down, it's just the factor that's related to the solvent itself. So the Kb is kind of unique for every solvent. So if we're working with water, we'd have to know the Kb of water or the Kf of water. But the other two things are things that we could figure out pretty easily. The molarity is just the number of moles per liter of solute. Mole per liter of solute. So this is just moles per liter. So how many moles of sugar do you have in that liter of water? How many moles of salt do you have in that liter of water? So you can figure out those pretty easily. The Kb and the Kf values we could look up. And then the N here is important because some molecules are more efficient than others. So it's kind of depends on how many molecules you have in solution is going to affect this. So if you have a very high concentration of molecules in solution, you'll get a greater effect than if you have just a small number of molecules in solution. And that's what this N is here. So if you look at various different elements and how they go into solution, different molecules will distribute themselves differently. So like a NaCl molecule, when you dissolve that in solution, it forms two things. It forms Na plus ions and it forms Cl minus ions. And both the Na pluses and the Cl minuses interact with the water. So one NaCl molecule will actually interact with has twice as much interaction power with water as a single NaCl, because all the Nas can interact and all the Cls can interact. Versus if you had something like an MgCl2, we still get the Mg molecule, but we also get 2 chlorines per molecule. So now we have one MgCl breaks up into one Mg and 2 Cls. So there's actually 3 ions in solution here. So ionic compounds, you get a number of ions equal to the number of molecules in the compound. The aluminum compound down here, 1 aluminum ion plus 3 fluorine ions. So now we have 4 ions in solution right here. So we got 4 ions here, 3 ions in the second case, 2 ions in the first case. But these are all going to interact with water. So if you have lots and lots of ions in solution because your molecule breaks up into a lot of small ions, that's going to have a bigger impact. So if you had 1 mole of each of these, if you had 1 mole of NaCl, you would have 2 moles of ions. If you had 1 mole of MgCl2, you'd actually have 3 moles of ions. Or if you had 1 mole of AlF3, you'd end up with 4 moles of ions. So this is going to have a really big impact because every mole actually has 4 moles of ions that are there to disrupt those hydrogen bonds and to cause the boiling point to raise and the freezing point to drop. Compared to something like this molecule down here, which is a molecular compound, which means it doesn't break up. So this one only has a factor of 1-fold. So if you had a mole of this, you'd only have 1 mole of molecules to interfere versus having 2, 3, or 4 moles. So depending on what you dissolve in the solution, you could have a really big impact. And that just has to matter with how do things kind of go into solution, how many ions do they produce, or do they not produce any ions at all and they just stay as a single molecule like the first, like the bottom one there. So that's going to impact how much stuff goes into solution, and that's going to impact actually how these go together in the end, and what kind of impact it has on the boiling or the freezing point. So this is just showing from a molecular standpoint kind of images, right? So if we have an NaCl molecule, it actually breaks up into an Na and a Cl, versus an MgCl2 breaks up into 3 ions. But a sugar molecule just stays a sugar molecule. So you only get 1 molecule of effect versus 3 or 2 molecules of effect for these other 2 molecules here. So that's important to know if you were to figure out, like, what sample is going to have a bigger impact on a solution. The sample that gives you more ions actually gives a bigger effect than the sample with fewer ions, assuming you have the same concentration for all those. So 1 mole of this sample gives you 1 mole of ions, and 1 mole of this sample would give you 3 moles of ions because those moles are going to break up into an Mg and 2 Cls, versus here that mole is only going to stick together and give you just 1 molecule. So this was just a kind of quick example calculation that we could actually figure out. Like if we wanted to kind of prevent water from freezing and we had a sample that was 1 molar of salt water NaCl, we could actually figure out, what temperature would this sample freeze at. So we just take, and they gave us the Kf, which was nice of them. So the freezing point change is just N times Kf times the concentration. So we got a 1 molar sample here. So that's our concentration. We have our Kf over here, and we have to figure out what N is. And since NaCl breaks up into Na plus and Cl minus, that's 2 things. So this is going to give us an N of 2, versus some other molecules may give us different numbers for N. And then you just plug everything in. So N is 2, Kf is 1.86, concentration was 1 mole per liter. And actually what's nice about this too is our moles cancel out. So 1 mole over here cancels out with 1 mole up here. And we get a change in temperature of 3.72 degrees, which means that normally water freezes at 0 degrees. And now this sample is going to freeze at minus 3.72 degrees. So this is going to freeze at a lower temperature than normal water would. It freezes at negative 3.7. So if the temperature was 0, regular water would freeze. If the temperature was minus 1, regular water would freeze. But this sample won't freeze until we get down to basically minus 4 degrees. So if the temperature is minus 3, this is still a liquid, which is safe which is good for us, right? We're driving along the road or walking along the road. We'd rather walk through puddles or drive through a puddle than drive across some ice. So if it's only minus 3 out, we'd be okay. This would still be this wouldn't freeze yet, and we wouldn't have to worry about getting any ice to slip on. So the new freezing point's now 3.72 for that sample. But you could use other types of salt too. So if we used MgCl2 instead, slightly different salt, even if we kept the concentration the same, if the Kf stays the same, we have a new K number here. So now, because the N was valued 3 instead of 2, now we have a new temperature, and this sample, 1 molar, actually freezes at minus 5.5. So the other sample would freeze at minus 4, the other sample would freeze at minus 5. This sample doesn't freeze till minus 5.5. So if you knew the temperature was going to be -3, maybe you'd use the NaCl solution. But if you knew the temperature was going to be -5, you wouldn't be able to use the NaCl. You'd have to use a different compound. And that's why some cities, especially colder cities or cities that are worried about their sodium impact, if they have a lot of reservoirs, they'll use other things like calcium chloride or magnesium chloride because they have slightly different freezing prevention capabilities for those different molecules, partly because the MgCl2 has a 3-factor instead of a 2-factor for its freezing point control. So you can kind of see here, right, depending on what solution you had, if you had regular freezing water, it would freeze at 0 degrees. But then as it cools down, water would freeze at 0 degrees. NaCl doesn't freeze till -3.7. MgCl solutions don't freeze till -5. So if your city was going to be in the -4 range, you don't want your water to freeze. Maybe you're going to go with this sample here of this MgCl2, versus if your city's only in the -2 range, maybe be okay with just the NaCl because you don't need to worry about it ever getting down to -5. You're only worried about it getting down to -2. And the reason this happens is because the salt molecules are blocking water from forming that crystal shape. So when water freezes, you have to have all these molecules like kind of perfectly spaced out. You want to have perfect hydrogen bonding, perfect hexagonal shape. And that actually requires a pretty good amount of distance between your water molecules because actually as those hydrogen bonds form, they actually put the molecules a little bit farther apart from each other. But if we had a bunch of NaCl's or MgCl's or any ion in solution, it actually blocks those bonds from forming. So I try to line up all my water molecules in just the perfect shape and have that really good structure, but there's a sodium in the way right here. There's a chlorine in the way over here. There's a chlorine in the way over here, and that prevents the water from kind of forming that perfect crystal shape as quickly. And if it takes longer, it slows it down. And when water slows down, that's the equivalent of having a lower temperature of freezing. So water is having a hard time kind of manipulating and rolling into just the right spot to form these really good hydrogen bonds. And because it takes longer for that to happen, the water has to cool down a little bit more. And that means that water with salt in it has a lower freezing point than water without salt. And therefore also, the more salt I can add, if I can add more salt molecules, that's going to make it even harder to freeze because there's even more molecules to get in the way and make it freeze even slower. So the more molecules you can get in the way, the more molecules you can add, the more you can disrupt this process and slow everything down. And also, depending on what you add, so either adding more molecules or adding molecules of a different type. Sodium does this, Mg does this, any ion can do this because all they're doing is they're getting in the way of the molecules. So it doesn't matter if it's a sodium atom or a magnesium atom or a chlorine atom or a sugar atom molecule or a salt molecule, no matter what you add, even if it's a large molecule like an ethanol molecule, what they're doing is they're blocking the water molecules from getting close enough to each other and freezing. And the more molecules you can add, the more disruption you're going to get. And that's why we need the concentration for figuring out the freezing point change, but also the amount of material that's there in terms of whether it gives you 1 atom or 2 or 3 ions. And the same thing happens for boiling, but a little bit different effect because rather than disrupting the formation of those bonds and kind of forming the perfect molecular structure here, what happens with water molecules when they boil is that all these molecules are hanging on to each other. And if a molecule tries to escape, then you need to then you hang on, and the other molecules hang on. And if it tries to escape, they go, no, 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 don't go anywhere. We got you. We're holding on to you because we have all these connections. But in a solution with more molecules, there's even more stuff to hang on to. So now not only are you being held on to by the blue dots of the hydrogen bonds, you're also being held on to by all the positives and negatives around as well. So there's even more things holding those water molecules in place. And you can kind of think it like a human chain. Rather than having just 1 or 2 people hanging on to each other like over here, there's lots more people hanging on this side over here. And this is going to be a much stronger connection. If you try to grab one person out of this chain here, everybody's arms grabbed onto each other. There's a lot more force, a lot more hanging on the molecule with the salts in it than the molecule with just the water molecule. So these groups going to hang on okay, but not near as well as this group over here. So because this group over on the left side or right side over here has all those extra bonds, all those extra ions, all those extra molecules holding on, the more molecules you can add, the more chlorines, the more sodiums, the more magnesiums, the more sugars, more things to hang on to the water molecules and prevent it from breaking away and going into solution means you have to give more energy or a higher temperature, and it takes more energy to boil water that has lots of stuff hanging onto those waters and helping them hold in place than a molecule that just has a few. So that's why water boils at a higher temperature, because all these extra molecules that are hanging onto each other. So that's why these happen. That's the colligative properties of solutions in terms of boiling or freezing points. And that's why we add salt to concrete to prevent snow or ice from forming, because we want to make sure that things don't become frozen. So we want to keep our streets from freezing and causing people to slip on and slide. We want to prevent the sidewalks from freezing, keep people from sliding, because it's a lot easier to walk across a liquid than a solid. So by lowering the freezing point of water so that water doesn't freeze, it stays a liquid and people don't get hurt. So we got 3 examples here of 2 different samples. So depending on what the temperature is going to be projected to be, right, water freezes at 0 degrees. So if it's 1 degree outside, no problem, we don't have to worry, the water is going to be a liquid. But if we live in a place where the water gets down to -1 or -2 degrees, our water is going to freeze at 0. We don't want to be in a situation where the water freezes at -2. So we add things like these different salts molecules here, and that keeps the water from freezing at -2 degrees. But at some point, we're going to get to a point where this one gets surpassed. So if we go to -4 degrees, this one doesn't work. But if we get down to -4 degrees, this one's still okay. So depending where you live and what the temperature is, you might have to use different types of salt materials to prevent the water from freezing. So for here, right, the water is going to freeze, but this water is still in the liquid state. So we're still in the liquid state for water with NaCl. But if we go even colder, now we're below the freezing point of regular water, we're below the freezing point of salt water, but we're not at the freezing point of calcium chloride water. So depending on what temperature you're at, depending on what system you're at, you'll want to choose a system where your water stays a liquid no matter what the temperature is. So if that means going at this range here, there's a range where you can't use sodium chloride, but you can use calcium chloride. There's a range where you can use both. And depending on what system you're in, what temperature system, you may have to be at this range, or you may be able to get by with this. But that's just a city planning issue. But that's why there's different types of salts that you can add to the sidewalks to prevent water from freezing, to kind of adjust for those different effects and temperatures. So that's one really big factor for water. And then the other thing that water can have in terms of colligative properties is this idea of osmotic pressure. And how does a solute or a solvent change the amount of pressure and the amount of molecule motion in water? And this is part of the reason why it's important that we drink pure water and not salt water. But if we drink too much pure water, we can have problems. So dehydration from drinking salt water has to do with basically how many molecules of water are in your sample. And if you look at like a sample of pure water, nothing in it but water, you can basically fill that container with water molecules, which we've shown here in blue dots. But if we were to take that same container and start adding salt to it, the salt molecules are going to start taking up space that the water molecules would take up. And you actually get less water molecules per area of sample per volume than you do in a pure sample. So if we look over here, right, this sample on the right, left right here has got 1, 2, 3, 4, 5, 6. That sample's got 12 water molecules in it. If you look at the sample on the right side over here, this sample's only got 8 water molecules in it. So even though they're both water, by adding salt to our water, there's actually less water molecule per area than in a saltwater solution than there is in a pure water solution. And if you took those 2 solutions of water, one with more salt than the other, and you're able to put a barrier between them that allows the water to go across but leaves the salt behind, and these types of barriers exist in your cells and in your body all over as ways of letting water across membranes, what's going to happen is water is going to try to go from the high concentration, which is over here where there's 12 molecules per area, to the low concentration because the water molecules want to be the same number on both sides. So what happens is water goes from the 12 per side to the 8 per side. So now there's 10 water molecules on each side of this barrier, even though this sample's got lots and lots of salt molecules in it. And that's why if you were to drink water that had salt in it, you would actually start to lose water. Even though you're drinking water, you would actually begin to lose water because inside your cells is more of a pure water system. Outside of your cells is a saltwater system. So there's a net motion of water from the inside of your cells to the outside of your cells. So even though you're drinking something, you actually start to become dehydrated. And this is really important for preventing dehydration or for treating people that have been treated with salt water, because if you drink too much salt water, if you're exposed to too much salt water, you can actually become less hydrated than you were if you hadn't drank that material to begin with. And that's all because the water molecules are trying to equalize the numbers so that there's the same number of water molecules on both sides of the barrier. The salt can't go from here to here, so rather than moving the salt from one side to the other, it moves the water molecules. So you get this effect of water moving from one side to the other, and then you actually get a net loss of water in this case here. So this is just showing it in another way. If you had a cell which had a lot of pure water in it, basically a low salt inside and a high salt outside, the water would leave the cell and the cell would become dehydrated. And if you take some red blood cells and you put them in a cup of salt water, you'd actually see them shrink down like we show in this little cartoon here. And this is really important for people when they're getting IVs or when they're getting transfusions. You have to make sure that the level of salt in their blood and the level of salt in their cells and inside their blood cells is matched. Otherwise, their blood cells will start to dehydrate and you can cause some real bad problems. And this is just some examples here of blood that's in different solutions. So what's called a hypertonic solution is when you put these into a high salt. So high salt is called hypertonic. And that's where water is leaving those cells because those cells have been put into a high salt environment. There's very little water outside the cell, and the water leaves those cells and goes into the blood to try to lower that salt concentration, equalize the water levels. And this would be really bad for somebody getting an IV because all the water would drain out of their cells and their cells would start to dehydrate. Opposite is just as bad. Actually, putting cells into a pure water solution is going to cause all that water, so a low salt condition here or pure water, now there's more water outside than there is in, and all that water rushes into those cells, and those cells will keep getting bigger and bigger. And just like if you take a balloon and you keep blowing, 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 and it pops, cells can do that too, and that's equally bad. So equally bad would be getting an IV of pure water. Not enough water in the not enough salt in the blood, too much water, your blood cells would start to pop. So this is bad because the cells dry out and they crinkle up and break, and there's not enough blood for you to get oxygen. This is bad too because now the blood vessels are going to start to pop and break, and there's not enough blood to give you oxygen. So either of those two are bad for an IV transfusion. What you want is a case where the amount of salt and materials in the blood is the same as the amount of salt and materials inside the cells. You want a condition that's called isotonic, so that the water does go in, but every time a water goes in, another water goes out. So there's no net motion in or out of the cell. And that's the kind of case where we want to have here. So that's the ideal situation, an isotonic solution for those. And these are just kind of 3 examples of each one of those kind of showed out. So we already talked about if you have too much water in the cell compared to outside the cell. And the reason you have too much water in the cell is because there's salts and stuff in the cell. But if there's more salt outside the cell, the water is going to go from the high water environment to the lower environment, because if there's high salt outside the cell, that means there's a little bit less water. The salts are taking place of where some of the water molecules would be. So the overall water concentration is a little bit low compared to the outside of the cell. And that's why the water leaves there. And that causes the water to dehydrate. So cells dehydrate when that happens. An isotonic solution, basically the water inside and outside is the same. So any motion of water is equal from one side to the other. And then the hypotonic is the opposite effect. So if you have water that's pure water, so if you drank a lot of really pure water, been drinking a lot of distilled water, or drinking just too much water, you might get to a case where there's less salt outside the cell than inside the cell. So the cell now has more salt than the outside. That means that there's actually more water outside the cell, and that water therefore tries to go into the cell. And cells can only hold so much water, and more water goes into the cell, more water goes into the cell, and eventually the cell swells and bursts and pops. And that's not good for you either, because that's too much water, and that's going to cause a problem. So this is sometimes called water intoxication. Drinking too much water can be just as bad as drinking too little. So dehydration, not drinking enough water, is bad. Overhydration is equally bad, because too much water also causes a problem where you can have too much set water in your cells, and your cells start to burst and pop, and that's equally bad for talking for your samples. And that's why it's bad for you to drink salt water. So salt water is not very good for you, because if you drink too much salt water, then you're going to have high amounts of salt water outside your cells. And that means that there's very low amounts of water in your cells. And the water goes from the high water environment to the low water environment, and it dehydrates you. So having salt water as a drink is bad because it's going to dehydrate all the water in your cells. The water is going to leave that high water environment of the cell and try to move out into the low water environment to try to equalize itself across both sides. But what if you're stranded in the middle of the ocean? And if you're ever on a boat and you ever sit around and you look in the life rafts, there's actually kits on the water boats, because right, if you're in the middle of the ocean, all the water is salt water, and it's not safe for you to drink salt water. It would dehydrate you. But if you go out to look on a life raft or anything like that, there's actually usually these little solar cells, and you can get these for your survival kits for your house too. But what this does is this is a way of making salt water drinkable. So the ocean has a lot of salt water in it. The ocean's full of salt water here. If you were to take some of that water from the ocean and put it into this little bubble thing, what this is it's a little balloon. It floats on top of the water, and it has water inside it that you've put in here. And as the water heats up, just like if you take a plastic bag and you put it out in the sun, the plastic bag, the water will slowly evaporate, and it goes as far away as it can. So water is always evaporating. But because the water is evaporating in here, just like if you take a pot of water on the stove, you'd see water start to steam up on the top of the lid. Same thing's going to happen here. Water gets on the lid, and then because it's a cone shape, the water kind of runs down the side of the lid, and there's a little lip on the side of this container right here, and the lip right here will collect the water, and the water in the ring right here will have pure water, versus the water down here in the pool has salt water. So salt water here, the salt doesn't evaporate, but the water does, and it becomes pure water around this little lip. And you only get a little bit. You only get a couple milliliters of water at a time, but that's enough to give you to sip kind of. So there's usually a little straw or a little syringe or something attached to these that you can use to kind of pull the water from the rim to give yourself a little bit of a sip of water. And that's enough to keep you from being dehydrated if you're stranded in the ocean. This is a way to kind of give yourself some pure drinkable water. And you can do this for anything too. If you had one of these in your house for if you're stuck in the middle of the woods, as long as you're in a place with lots and lots of sunlight, you can use this to get very small amounts of water to keep yourself from getting sick and dehydrated, because you can't drink the ocean water, that's bad, but you can drink the water from the solar still. And then just to kind of wrap up this idea, what about things like sports drinks? Because if you look at a sports drink and you were to look on the label, it usually does list either sodium or salt. And sports drinks do have some salt in them, which we already said is bad, right? So salt water is not good for you to drink, because the salt water is going to cause the water from inside your cells to leave and dehydrate. But if you're an athlete and you're competing a lot and you're doing a lot of work, you may be drinking too much, and you're drinking lots and lots of water. You could actually overhydrate yourself. So you may want to drink a little bit of salt water or a little bit of Gatorade to kind of put yourself in this condition where the water in and the water out are equal, because we don't want you to get into this case where you have too much water, which can happen too. So there have been a few different cases where people have done things like marathons, or they've been in a big race or something, and they drank too much water. They drank gallons and gallons and gallons of water, and they actually got into a case where they had more water outside than inside their cells because they were drinking so much water and drinking so much that they lowered the concentration of salt in their blood so much that the salt concentration and the water concentration was lower inside the cells, and their cells started to swell and burst. And there's been cases where people have gotten really sick, especially some of these really high, big marathons where people are running really long distances and drinking a little bit too much water, not having quite enough other conditions. And the other thing that's really bad about water intoxication or hyponatremia is that the conditions are really, really similar for too much water and too little water. So if you drink too much water, you're going to be hot. If you drink too little water, you're going to be hot. If you drink too much water, you're going to have a headache. If you drink too little water, you're going to have a headache. You're going to feel like you're going to throw up. Both of them have the same kind of symptoms. And the only difference is that one person had too much water and one person had too little water. And the treatments are really different. So if somebody drank too much water, you give them a cracker with some salt on it. If they drank too little water, you give them water. So being able to talk to somebody, find out what's going on, and they say, oh, you know, this is really weird. I've been running all day, but I've been drinking tons and I don't know why I still don't feel good. It's not because they didn't drink enough water, it's because they drank too much water. So that's kind of an interesting thing that can sometimes happen with these races. And unfortunately, if you don't catch it, it can be just as fatal. So a few people have collapsed during races because they drank too much water. And actually, if you look at a lot of runners in marathons, a lot of runners actually overhydrate too much. And some of them are under salt watered and some of them are overwatered. So it's really important that you make sure you drink the right amount of water, but you don't want to drink too much either because there is too much of a bad thing. So the last thing of when we're working with samples like this with colligative properties is the property of dialysis. And this also takes advantage of the osmotic pressure and the fact that molecules will move from high pressure to low pressure or from a high water to a low water size, except now we're using a membrane that allows the water to go through again, just like before. So before, water molecules were able to transfer from one side of the membrane to the other. But if we go to a slightly larger size membrane that also allows small molecules to go through, they'll also go from a high concentration to a low concentration. So by going from a high concentration to a low concentration, we can allow certain molecules to move from one side to another and while keeping the larger molecules retained. So here we have an example where we have both large and small molecules. So we have some large molecules like this one here, but we also have some smaller molecules like these spheres here. But the membrane that we're using is a small enough size that the smaller molecules can go through from high salt to low salt. So just like the water is going to transfer from high water to low water or low salt to high salt, these salt molecules are now going to try to go from a high salt to a low salt concentration. And you can see that here, except the larger molecule gets stuck because it's not large enough to fit through the pore. So dialysis allows molecules to travel from one side of a system to another by allowing them to travel through these small particles. And that's a way of removing ions from a solution. You could remove salt molecules from a sample, but also keeping larger molecules retained that you may care about, like blood cells. So this would be a way of removing toxins from a blood sample that has very small toxin contaminants, but keeping all of the large molecules remaining behind in solution without losing any of the large blood cells. So that's kind of the end of this chapter. Hope you guys have a good week, and we'll talk to you later.